you able to hear me?
Yes, we can hear you.
Okay.
Okay, sir, we're live in YouTube. Shall I start?
Can you hear me?
Yeah.
Yes, I'm audible. You're audible, sir. You're audible.
And the screen is also fine, right?
Yes.
Great. Then you can go ahead.
Okay.
If you're able to see.
Just the PPT is yet to come, I think. It's showing loading.
Okay. Not yet?
No, sir. It's showing loading only.
Just a minute. Let me share it again. Okay.
Yeah, we can see your screen now.
Okay, great.
Yeah, but the PPT is loading.
Yeah,
right.
Great. Sir. Okay, I'm starting then, sir.
Great.
Okay, sir.
Okay.
Yeah.
So everyone, we are starting now. So good evening, everyone, to the Vertical 3, where we focus mainly on practical sessions of open and proprietary software. And again, welcoming you all to the 13th session as of today. Myself, Giri, one of the coordinator for Drug Discovery Hackathon. As usual, the disclaimers, please do not share any of your personal details and kindly refrain from your greetings. We accept all your humble greetings. We do not want to miss any of the important questions, and all your questions will be answered at the end during the Q&A session. So today we have on board the partner CRESSET. So today there will be introductory session, that is introduction to CRESSET science and software, and which is streamed both in MHRD Innovation Cell YouTube channel as well as in Facebook DDH 2020 page. And today we have speaker Dr. Stuart Foote-Clark. His PhD is in chemistry from University of Bath. He was also investigating the use of computational methodologies to study chemical reactivity. Later, he spent 20 years working for small biotechs as well as CROs, where he was having responsibility for developing and implementing their computational chemistry services to prospective and existing customers. Currently, he is a senior application scientist at CRESSET, and his responsibilities are training and supporting customers so that they can achieve their scientific goals using CRESSET's ligand-based and structure-based software solution. Welcome, Dr. Stewart, and over to you. And I also would like to invite Krishna Kumar, who is the country manager for CRESSET in India. So he will give a brief introduction about CRESSET, and then Stuart will take over with the presentation. So over to both of you. Thank you.
Yeah. So thank you, Giri, for the kind introduction. Good evening to all. Firstly, I would like to commend the organizers of Drug Discovery Hackathon for bringing together a scientific community and for providing a platform to discover and design an innovative solution for the fight against COVID. It's really a great initiative. I would also like to thank the organizers on behalf of CRESSET for the opportunity given to us, and we are excited to be a part of the Drug Discovery Hackathon. So as Giri said, I'll begin with a small introduction to CRESSET and then hand over to Dr. Stewart, who will give you an overview of CRESSET science and solutions. Stuart, can you share your screen?
Okay, let's do that.
Thank you, Stuart.
No problem.
So CRESSET was founded in 2002 by Dr. Andy Winter and Dr. Mark Mackey. CRESSET develops solutions that help researchers to discover and design molecules faster. We do that by developing technologically advanced software scientific platforms, which are used by researchers around the world. We also provide discovery services based on CRESSET technology and deliver projects for our customers. Top 15 of the 20 top pharmas use our software. but that doesn't mean it is restricted to pharma companies. Our software usage cuts across different industry verticals like biotech, agri, flavors and fragrances, academic and research centers. Our customers base spans across geographies, and we have hundreds of customers in North America, Europe, India, China, Japan, and Korea. We have also delivered 250 plus projects to our customers globally. We support the chemistry team researchers with our ligand-based and structure-based software solutions and services. We are a growing company and believe in bringing new science and technology to our customers. We have about 35 plus staffs across 3 continents. Majority of them are PhD holders who support our customers globally. We have our headquarters in Cambridge, UK, and have remote offices in North America and India. We also work with partners in India, China, Japan, and Korea. Neotel is our partner in India, and they help us to support our academic customers. So they'll be working with the participants in hackathon and supporting them as well. We also have an application scientist in India, Dr. Anand Balupuri, who will be your main contact during the hackathon process. So he will be supporting you with all the question and answers session. Over to you, Dr. Stewart.
Thank you very much, Krish, and welcome everyone. I'd just like to take a brief opportunity to thank the organisers for giving us the chance to speak at what is going to be a very exciting time and an event that is clearly going to potentially lead to some very interesting science. So it's a real pleasure to be part of this process, and I hope today is useful for the people who are taking part. Okay, so what I'm going to do today is a number of things actually. So first thing I'm going to do is I'm going to introduce the science behind the CRESSET software, and I'm also going to introduce the software available as well. In particular, I'm going to sort of concentrate on the structure-based drug design software that we have called FLAIR. And there, what I'm going to do is I'm going to briefly give an overview of the ligand design focus of the software. I'll then go on to talk about how we sort of model the biomolecules within the software. And then once we've done those 2 things, we'll talk about the docking techniques available within FLAIR, as well as describing the electrostatics between the ligand and protein and how complementary they can be, and how we can visualize that. After that, I'll have a quick chat about how we look at binding site water analysis, and from then on, I'll also talk about some of the MD simulations, but dynamic simulations that you also have in FLAIR. And then I will just touch on right at the end about the ability to use Python within FLAIR, because FLAIR is based on the Python program. After we've finished with FLAIR, what I'm going to do is I'm going to give you a brief overview of Spark, which is our bioisosteer replacement program. And then after Spark, I will also give a very brief introduction to our software called Forge, which is our ligand-based design tool, which I will briefly talk about at the end. So let's get started then. Let's think about the science behind CRESSET. So CRESSET is based on the science is based on something called the Z force field. This is a force field that was designed by us. Specifically, it was set up by Dr. Andy Winter. And so this is an extended electron distribution force field. And basically, it's the difference between this and many other force fields is that with many other force fields, the atoms are described so that they have atom-centered charges on them. But what you find is that that's good for many applications, but for things like sort of secondary effects like pi stacking effects and p orbital interactions, those sort of atom-centered charges are not good enough. And so what we need to do is change the description a little bit. And so what we do with our force field is we split the charges up into two parts, if you like. You have the sigma part, which is still based on the atom centers, but then the pi cloud is then defined by some Z atoms, which in the first case here is they are located above and below the aromatic ring. In the second case here, they are above and below the carbonyl group just here. And what this allows us to do is it allows us to start to be able to model effectively things like pi stacking interactions and charge pi interactions as well. Some of these sort of more difficult things that often require just quantum mechanics to describe. So it's a fully functioning molecular mechanics force field. So you can do all the great things that you do with traditional force fields. So you can do minimizations, you can generate conformations, and you can do many other things. The one thing we can't do is dynamics. Let me give you a brief explanation of what the force field does. So here's an example of sort of how the ligands get described with the said force field. So on the left hand side here we have methylbenzene, and methylbenzene here you can show in sort of the Z representation where the positive and negative charges are. So we basically have negative charge coloured in light blue here and positive charge coloured in red. And what you can see here is that the negative charge is concentrated above and below the ring, with a ring of positive charge around the molecule. So in the second case here, we've added two fluoro groups. And what that does is that because the fluors are electronegative, the fluorines suck out or extract a lot of the electronegativity from the ring. So all the electronegativity sort of becomes one-sided, with the positives with the positive side being on the opposite side. And so what you can see here is the effect of adding halogens to the electronic distribution. And then we can actually look at a different halogen, sort of adding chloro groups. And what we can see here is that actually the electron withdrawing compared to the fluoride, electron withdrawing is not quite as extensive, and also chloro groups donate their sigma electrons into the ring. So that means you end up with these sigma holes just here, which the force field can describe adequately. Moving on to something a little bit more complex, what this means is this sort of description allows us to look at more complex ligands like sildenafil here, and we can compare how sildenafil looks with other similar looking molecules, and we can determine actually in terms of the electronics which molecules look more similar than in the other cases. And sometimes it can come up with some very surprising results, so that actually what looks interesting or what looks very similar from a 2D representation actually is quite different when you start to consider the electronics. So this is where the CRESSET technology becomes very useful. Okay, so that's why we've been just talking about ligands, but the CRESSET description can actually be extended to proteins as well. So actually, on the left hand side here, what I've got is a ligand bound into a protein, and the protein solvent accessible surface is defined by the said sort of positive and negative regions in space. And what we can do is we can look at the electronics of the binding site, and we can compare the electronics of the ligand as well, and we can start to understand at what point do we get electrostatic clashes? What point do we get favorable electrostatics between the ligand and the protein? And I will talk about this a little bit more with the electrostatic complementarity, but just to give you a flavor, we actually can recolor this so that the favorable electrostatics are colored in green, and the sort of electrostatic clashes, if you want, are colored in red. And this allows you an opportunity to look at where there is a good fit between the ligand and the molecule, and where there could be potential improvement as well. For example, is there a functional group which is actually contributing to an electrostatic clash? Maybe if we change that group, we can make that more favorable. One last thing I want to talk about with regards to the science is what we talk about. Sometimes talk about field points. So at the moment, I've been talking about molecular interaction potential surfaces, and these are beautiful things, and they're quite easy to calculate. But what happens is that's great for one or two molecules, but if you want to align lots of molecules, you need to have something which is a bit more efficient in terms of calculating those features for all those molecules. So what we do actually is we take the electrostatic interaction potential, and from that we calculate the most important points around that molecule in terms of where the most negative point is, where the most positive point is, where the most hydrophobic points are, and this gives you so you reduce down the 3D structure into the salient, the important salient features for the molecule, and this allows us then to look at many more molecules and to compare their functionality with one another. Okay, so what I'm going to be looking at today is we as a company, we have 3 desktop tools. We have firstly on the ligand base side we have Spark. Now what Spark does is it's a bioisostatic replacement program. So that's basically where you have a structure, but actually you want to replace the core scaffold, maybe to do some patent busting or to give you some new ideas, or maybe some to change an R group on the particular molecule you're looking at. So you would use Spark for that. The other ligand-based tool we have is Forge, and in Forge what we do is we have functions that allow people to build quantitative structure activity relationships, to actually look at the SAR analysis both qualitatively and quantitatively using a 3D molecule view, and it allows us to build up a hypothesis for the bioactive conformation as well. So this you would probably use Forge when you don't have knowledge of your protein structure. The vast majority of the presentation today, however, will be on the structure-based drug design program we have called FLAIR, and that's where we will be looking at the fact that it's a ligand design. It has a ligand design focus associated to it. We also have sort of description of electrostatics, which I've just briefly talked about, and we can also look at the water positions and the stability analysis of those water molecules, and it has a number of other features, including, because it's a Python-based system, the ability to be customized. So if you know Python, you're able to incorporate your Python scripts within FLAIR and also edit the day-to-day working of the program with Python. So this brings me on to the next stage of the presentation, which will be looking at FLAIR and giving you some basic introduction into the facilities that we have in there. Okay, so FLAIR is CRESSET's workbench for structure-based drug design, and it's it basically you can use it to analyze proteins and in form of new molecular designs. We've incorporated some really good cutting-edge science. We briefly talked about electrostatic complementarity. We can also do 3D resin is basically the description of the binding site water molecules. We also have the ability to customize force fields in FLAIR. So if you're doing some electrodynamics, we are able to get the users to generate some custom torsion parameters for their particular molecular systems, which might not be appropriately described by the more traditional force fields. In addition to that, we have the ability to dock and score, to do some ligand-based alignments, and to also do some electrodynamics as well. So I will also start to show you that the interface is modern, and we've designed it in such a way so it's user friendly, so that there's hopefully a low barrier to use, so that anyone who has an interest in computational chemistry, be they medicinal chemist or computational chemist alike, that they can start to use the program relatively easily, and with the aid of support if needed. So if anyone gets stuck, then they're more than welcome to contact our support, and we will be able to help them out. But we're hoping that by having such a friendly user interface gives people a good opportunity to get started. So here is the brief introduction to the interface. So what we have here is a main 3D screen right in the center there. To the left-hand side here, we have the ligand part of the interface. So this is a ligand table, and so if you import your ligands as an SD file, that this is where they will be loaded into. On the right-hand side here, we have a proteins window. So if you download some proteins from the PDB file, this is where they will be located. And then we also have some other functionality as well, which I'll briefly describe, such as storyboarding, which will allow you to manipulate the 3D window and take a brief snapshot, which is great if you want to then save the FLAIR project file and share it with your colleagues or customers, so that you can then describe specific parts of your modeling. So let's move on to the ligand design focus. One of the important parts of the ligand design focus part is to make sure that users can see the interactions between the ligand and the protein. And in the main home tab here, we have a contacts button, and that contacts button allows the scientists to show the interactions between the ligand and the protein. But actually, if you expand the contacts bar, what you can see here is that the scientists can actually turn on and off various interactions that they are either not interested in or interested in seeing. Just to the bottom here, we have sort of a matrix system, and at the moment, what you're seeing is the interactions between protein and ligand and water and ligand, and these larger squares here represent the interactions between protein and ligand are given in a slightly thicker dotted line here. In the software, we have a ligand tab, and the ligand tab gives you access to everything you'd want to do with the ligand. You can basically edit the ligand. You can look at the table, the ligand table. So you can sort the ligand table on any of the columns. So by like you would do in Excel, you would double click or click on the particular title, and you will then sort based on that title. Each ligand can be associated with a particular protein. So So basically, you can define which protein belongs to which ligand. You can change the visibility of the ligand. So say you've done a docking experiment and you want to compare the dock solutions to the crystal structure, you may want to keep the crystal structure permanently turned on as you scroll through the docking solutions. So you would do this by changing the visibility of the ligands by pushing on this square here. The other nice thing about the ligand table is that the scientists can actually divide the table into specific groupings, what we call roles, and this allows you to divide your system up so that you can keep control of what you see. So for example, if you brought in a crystal structure ligand and then you did a docking, then you could move the docking results to a new role, and so you could have two separate roles, one for all the crystal structure ligands and one for all your dockings. And then if you started doing some design work, you could then have another role for all your designs. So it keeps from a user's point of view, it keeps everything in a nice ordered fashion. We've also, when you bring some ligands in, we also calculate some simple physical chemical properties, things like S log P and TPSA. And we also have the ability to add tags to particular molecules, so that you could, for example, again going back to my crystal structure example, you could actually define crystal and add that as a tag for all your crystal structure ligands, and docks for all your dock solutions. That's another way you could look at the difference there. And we also have the ability to add notes to the table as well for slightly longer notes for each of the ligands. So we've also in Flare got a sort of iterative molecular design, and we've got sort of dedicated menus that allow users easy access to edit a ligand, and you can either edit the existing ligand, or you can edit a copy, or you can then duplicate it first and then edit the duplicate. Completely up to you and how you feel most at ease with. So when you edit a ligand, that brings up a new tab on the program, just an editing tab here. And what this allows you to do is it allows you to add various groups to the ligand. So that could be atoms or functional groups. And while you do that, the rest of the system is still visible. It's slightly grayed out, just to show the scientist that is not being edited. It's only the ligand which is being edited. And as you're editing the ligand, you can actually change how the rest of the system looks as well. So you can turn off the ribbons, you can add the contacts or change the protein that you're seeing. And that is can happen while in the editing mode. Another really nice feature that we have is radial plots. Now, very often you have many features of a molecule which are favourable, and you want to find, if you like, a feature, basically a molecule which sort of hits all the features in the right place. So in terms of making sure that you have the correct molecular weight, for example, the correct number of atoms, the correct S log P, you can basically set up a multi-parameter function so that all of these can be incorporated into a single function, which of course then can be sorted in the table. So you can do that for any of the numerical numbers that are already in Flare. But of course, if your SD file also has values from other programs, activity values, then you can also incorporate those into the radial properties. So the other thing which we briefly discussed was storyboarding. And so with storyboarding, what you can do is you can set up system where you look at particular molecules in a particular way. So here we've got electrostatic complementarity surface on the ligand, and I've got the protein surface in a slightly different description, and I can take several snapshots looking at slightly different things, and if I just zoom in on this slightly, what we have here then is sort of different pictures at each stage, and then for each of those pictures you can add notes, so that you can save that as the project file, and then your customer or your customer or your person you're working with can then actually come back and look at it and understand what you're trying to show. So the another thing that we have is filters, and this is something that's quite nice as well, in that very often as the project develops, you're going to get lots and lots of molecules in this ligand table, and very often you'll want to try and hone in on particular ligands which have specific features, and that could be features like what the title of the ligands contain, what the various smarts options. So you might want to have something with a benzene ring, for example, or you might want to have a filter on electrostatic complementarity as well. And so the scientist can set up any sort of complex filtering process, and what happens is when that filter is applied, what you'll see in the ligand table here is that actually there are 11 in this particular row here. There are 11 molecules, but one is hidden due to the filters. So that means that there are 10 that are visible. And what you can do is you can also, as well as set up the filters for the project, you can actually export that, so that if you wanted to use the filters for another Flare project, you can just simply bring those in from this project. And what happens here is that these buttons here allow you to toggle the filter on and off temporarily. So at the moment, a red button would represent inactive, and you would then sort of push it to activate it to make it green. So you can make these filters temporary, so that you can find hidden ligands again that have been filtered out by the filter. The other thing which is really nice is the drag and drop support that we have. So what we're trying to do is make it as easy as possible for people to get molecules in and out of Flare for their use. And so one thing you can do is from a Windows Explorer, you can actually drag it's an SD file and a PDB file into the ligands and proteins table respectively, and vice versa. So you can actually move the protein into the ligands Explorer folder, and you can also move a ligand there as well. And you can also interchange what a ligand is and what a protein is by dragging and dropping into either the proteins window or the ligands window. And while I'm on this subject, you know that if you have access to drawing programs like ChemDraw, then what you can do is if you copy the ChemDraw object into your clipboard and paste into Flare, Flare will recognize that that is a molecule from ChemDraw and will prepare it appropriately. So let me briefly talk about confirmation hunt and align. So in Flare we have the ability to take a number of ligands and generate some confirmations for those ligands, and then align them to a reference molecule. And you can do this by describing them in either using the electrostatic and shape of the reference ligand to help to define the way in which the ligands are overlaid, or you can define it in terms of the substructure. So your reference molecule may have in common the substructure of all your ligands, and so you can do one or the other. You can also add protein chains as an excluded volume. So what that means is that if you want to align your ligands in the presence, so say your reference molecule is a crystal structure ligand, you can actually incorporate the excluded volume of the protein to ensure that all the alignments do not encroach on the positions of protein atoms. The other thing you can do is, if there are specific features that you think are incredibly important, then you can actually invoke a constraint, be it a pharmacophore one or a CRESSET field constraint, to ensure that any of the molecules which have those features at that particular point those features are adhered to, so that if those features are occurring within those molecules, they would be overlaid onto the reference ligand, having those features in place. So one reason why you'd want to do that is because having the ligands in one place allows you to start making comparisons between molecules which are very active and molecules which are not so active. You could start to understand what groups are contributing positively for the activity and what are detrimental to the activity. And you can also start to use that information to start to design some molecules which are different, but are set up to have a more ideal activity and property profile. And the other thing you can do is, once you've got those alignments in place, you can actually do a small amount of virtual screening from your desktop. And so the other thing which you can do is, by aligning those ligands, it means that you can also start to calculate each of those molecules and how well they fit into that particular crystal structure in terms of their electrostatic complementarity. So I think that concludes the ligands part of the presentation. What I'm going to do next is I'm going to start to talk about how we set up proteins within FLAIR and how they can be used. So again, we wanted to make sure that that the preparation of the protein is a very easy process for users, for scientists. So what we do here is we wanted to make it as easy as possible for people to basically download a PDB file from the internet, and then, so in this case we can download the 4ZLZ protein, and we can then FLAIR then sort of asks how you want to deal with that protein structure. But if you want to set it up for a drug discovery project from the PDB, you'll know that there are a number of things that need to be done to ensure that that happens. So what the scientists can do is they can define that actually what they want to have done on this protein is a full protein preparation. And what that will do is that sort of protein preparation will make sure that hydrogen atoms are added to the PDB structure, that the protonation state of ionizable residues are considered and appropriately charged and uncharged. It would look at also the side chains between glutamine and asparagine, because in crystal structures it's actually very hard to tell the difference between a carbonyl oxygen and an NH2 group. So the program automatically looks at the difference between the two conformations. And also, if there are very often in crystal structures, you get missing side chains because the electron density isn't there. So what the program can do is it will also add missing side chains in part of the preparation of the protein. Now, the other thing that it does is to identify what the ligand is and extract the ligand to the ligand table, and also define the binding site by default, which is a six angstroms around the ligand, but that is usable, a user-defined case, so you can define that to be more or less depending on the work that you're doing, and so by the time the protein is prepared, it's pretty much all the major errors should be sort of sorted out, and you should be ready to go in terms of getting on with your work. However, what you can do is, just to be absolutely sure, you can do a protein structure check, and what this does is that it just gives you a list of any potential issues that have come from the protein preparation, maybe because it can't be resolved for some reason, or maybe because you have edited the protein and have accidentally made a change that is not appropriate. So what it's looking out for is non-standard and modified residues. It's also looking out for covalently attached ligands. It's also looking out for residues with missing atoms, and any clashes between H-bond donors and acceptors are also highlighted, as well as Ramachandran violations and steric clashes. And if there's any sort of structure in connectivity issues with the standard residues, this will also be highlighted as well. And if the chirality of the residues are inverted, the program will alert you to that. I should also mention that, for example, if I was to do a project, one thing that I would do is carefully check by manually just looking at all the histidine residues, making sure that they all rotated correctly, they're all being protonated or deprotonated correctly, and also making sure that aspartates are deprotonated and glutamates are deprotonated. Just spending a bit of time on the protein just to make sure that things are sorted out. Now, another thing that you might want to do is your project might have a number of crystal structures for that particular protein. And if you bring them into Flare, what you will soon notice is that they are all in a different coordinate frame. But that's for a drug designer, that's not very helpful. So what you often need to do is superimpose all the molecules onto one another so that it's more useful to yourself. And you can do that within Flare so that for the proteins we've brought into Flare, you can in the alignment window here identify proteins that you want to be aligned, and you then once you've done that, you push the alignment tool, and that will align the protein sequences, and that will give you the sequence similarity table just at the bottom here. And once you're happy with the sequence alignment, you can then push the superimpose button. When you push the superimpose button, you then get an option box which allows you to define which of the proteins are the reference molecule, and the program will then align all the other molecules onto that reference molecule, and that should make comparisons between the proteins a lot easier. The other thing you can do is you can adjust the protein structure a little bit more, in that we've provided a mutate option in the proteins tab just here. So what you would do here is you would select a particular residue, and I am now going to mutate this to a histidine. So what will happen here is I say to the program I want this to be a lysine. The program will then replace the glutamine with the lysine, and and will then re-prepare the protein and make sure that that lysine is appropriately charged and is not making any clashes, and making sure that everything is in good shape. The other thing you can do with proteins is edit them. So just like you did with ligands, you can either edit picked atoms, or you can edit certain atoms within the protein. So if we go to the editing tab, you again get this temporary editing tab back, and again what you have available to you is the ability to change the atoms within the protein. So that pretty much brings me to the end of the biomolecular modeling part of the talk. So far what I've done is to show you in Flare the ligand descriptions and bringing the ligands into Flare, the biomolecular modeling within Flare. And now once you've done both of those, you're probably now ready to do something fun, and something, for example, docking. So what I'm going to do now is just briefly describe to you the sort of options we have for docking within Flare. Okay, so we have a number of docking methods available, and so one of the things that you can do is depending on the number of ligands you have, you can dock ligands very quickly to get a rough idea of how ligands bind in the site, or you can do if you've only got one or two ligands, you can define a very accurate docking option, and that is up to the user so that they can decide how fast or how accurate they want that docking to take place. We also have the ability to do something called ensemble docking. Now, ensemble docking is when docking starts to consider the flexibility of your protein, and I will talk more about that in just a second. We also have an option called template docking, and that's available both when you're doing a standard docking and doing an ensemble docking, and it's where you have a substructure that you know the binding mode of, and then you want to make sure that all your compounds which also have that substructure docked into that same position as your known molecule. And the other thing that we can do is covalent docking. Again, I'll talk about that in just a second. And we can also apply some docking constraints. So if you have hydrogen bonding requirements that you feel are absolutely necessary for the dockings to adhere to, you can enforce those before you start doing the docking. So let me briefly talk about ensemble docking. So ensemble docking, it comes about because a lot of docking algorithms out there assume that the protein is a rigid site, and that's in the real world is unrealistic. But if you also look at flexible docking algorithms, we've had a lot of feedback to say that actually flexible docking algorithms also give very unexpected results. And so what we've implemented in Flare is the ability to take known protein structures and we overlay them onto the same coordinate frame, and then the docking program then chooses as it docks which of the proteins it wants to dock into. So if you've got different protein structures within your project where the ligands are invoking a slight induced fit so that the conformation of those proteins are slightly different, what the program will do is that you supply the docking input with all the proteins you want to be incorporated into the ensemble docking, and as the docking progresses, the program will start to decide which of the proteins it's going to dock into. When you get the results back, then what you will see is that the top 10 binding poses will come back, for example, here, and you can see in just highlighted in the orange rectangle here that each of the the docking solutions have come from a different protein here. So some have come from the 4ZLZ protein, some have come from the 4Z33 protein, some have come from the 5P9J protein. So template docking is available for both docking and the ensemble docking experiments, and it's used so that we can seed a docking run with a known substructure, and basically it allows you to ensure that you get the docking solutions for your project for your ligands that you would like to see, and so what you get, for example, here at the top here, this is a normal 2D input docking conformations, and that's worked reasonably well. But if you use the template seed, then actually the dock solutions are a lot more together, and so it gives you more confidence in the dock solutions once you've seeded this template. So moving on to covalent docking. So covalent docking happens when you have in the active site you have a residue which can act as a nucleophile, and you have a ligand which has an electrophilic center. And very often when that happens, then the electrophile of the ligand will react with the nucleophile of the protein residue to produce a reversible covalent inhibitor. And so what we can do here in FLAIR is with these initially with these electrophilic warheads, we basically supply the docking program with these in the reacted form, and during the docking they are reacted to the reactive residue, and you generate a covalent species as the docking result. So here you have the covalent warhead on the left-hand side, and here you have the covalent species on the right-hand side, where in this case it's a cysteine has been reacted to, and the covalent docking program recognizes four main amino acid residues: cysteine, lysine, serine, and tyrosine as potential nucleophiles. So docking constraints that are set up so that in case, for example, in this case, you want to make sure that the hinge binding interactions are retained in all the docking solutions. And so what you can do is you can add an H bond donor and an H bond acceptor constraint, and when you do the docking, when you can also define the strength of those constraints. So if you find that, for example, in an initial test, you find that the constraint in normal doesn't adhere to the H bonding taking place, you can make the strength of the restraints much stronger, or you can make it a little bit weaker so that you give it a bit of flexibility. And once you've done that docking with constraints, you see that the dock solutions come back with the interactions that you're looking for. So that completes the docking part of the presentation, and I think that what that means is that we will now move on to discussing electrostatic complementarity. So I briefly mentioned earlier that that with the Z force field you can define your protein surface and your ligand surface in the electrostatic. So that again, blue is minus, red is positive, and we want to look at the interactions between ligands and proteins, and part of doing that is because it's an important part of the recognition and binding energetics. So it's quite important to think about this. It also gives you an understanding of the way ligands bind. Also, if you're designing ligands, it can inform you of what you want to develop, what you want to change, what is allowed to change, and it can also, in many cases, predict the activity of the ligand as well. So what we've done is to set up a dedicated algorithm which calculates not only the display of the electrostatic complementarity, but also set up a scoring function as well. And so if I just go to the right hand side here on the picture, what we have here is streptavidin, which is the protein, and the surface of biotin here. So what I've done here actually is to show you I've kind of rotated by the biotin 180 degrees, so you can see that this red positive surface on the protein corresponds to the negative surface on the biotin here. And while that's very useful, it's actually from an end user point of view, from a scientist point of view, it's actually very difficult to visualize that in any great clarity. So what we've done is to introduce a sort of color scheme showing you how complementary the electrostatics are between the ligand and the protein here. Now, by the way in which biotin binds to streptavidin, it's almost perfect. So that what you see here in terms of greens and reds is that the green represents the sort of favorable electrostatic points between the ligand and protein, and any red represents electrostatic clashes. So you have a kind of a gradual process of going from green to red. The more green you are, the more complementary your electrostatics are. The more red you are, the greater amount of clashing you have. So here's an example. So this is a ligand for mGlu-R5, and what I've got here is a 5-membered aromatic ring with a fluoro group on it, as opposed to just the 5-membered ring here. And what you can see here is that by adding that fluoro group, you basically add some clashing between the ligand and the protein into the electrostatics. You've got a serine residue here, you've got the backbone carbonyl here, so there's plenty of negative charge. So adding the electron withdrawing fluoro group is not benefiting you here whatsoever. So surprise, surprise, that's when you get to see the pKi, that actually this has a lower value than this value, probably because of this electrostatic clash. And if we look at the electrostatic complementarity score, you can see that drops a very little bit because of this addition of this fluoro group. Now another example is if we have a 6-membered ring instead, and we add a fluoro group to that 6-membered ring. And here it's a bit of a different story, because we have a slightly different orientation for the group, and it means that you have a much more favorable interaction between the ligand and the protein, and the electrostatic complementarity goes up, and it also follows that the activity also goes up. We published this as a paper last year, so this is the paper that was published, and here you can see many more examples. And what we've also shown here is how, if you plot electrostatic complementarity with the IC50 of the known molecules, that there is a good correlation between the two. So again, this is the paper if you're interested in reading a bit more about that. Okay, I now want to talk about 3D Rhythm. This is about when you want to talk about or want to consider the water positions and their stability within the binding site. And we use it again. We use our proprietary software, the said force field, to as the basis for the description. So let's think about the this example here. So this is again from Bruton's tyrosine kinase. So this is this 4ZLZ crystal structure, and this has a ligand bound into the binding site, and associated with that ligand is this water molecule here, and that makes an interaction with the ligand, but it also makes an interaction with the protein backbone as well. And so one of the things that that is quite interesting here is that the sort of question is, can we design a ligand so that it can displace the water molecule? Now what you can do is you can use 3D RISM to describe where in that active site, binding site, your waters are most energetically favored and which are most energetically disfavored, and that again ranges from green for favored to red for being disfavored or unhappy. And what you'll see here is that the water molecule here is also kind of a sort of grey in the middle, not really happy, not really unhappy, but it shows that actually if you do design a ligand to displace that water, then that is actually feasible. And that if you design that ligand with this so this is showing the 4Z33 ligand here for this crystal structure, and you can see that it's actually quite easy to displace that water molecule. So what 3D RISM allows you to do is it allows you to identify the water molecules that are loose or happy or unhappy, so that you can determine whether you can incorporate some of your ligand-based design work to incorporate the interactions that water is making. So let me go and move on to molecular dynamics within FLAIR. So when would you want to use molecular dynamics? So you'd want to use it when you want to look at conformational changes in proteins, or perhaps when you want to look at the stability between protein and ligand complexes. So the implementation within FLAIR uses the OpenMM package. So this is a public domain piece of software which we have brought in, and we have made what we want to do is make a user-friendly interface so that the scientists can use this again relatively easily. The force fields that you have available to you are amber-based, so they're the general atom force fields, GAF and GAF2. We are also CRESSET is also part of the Open Force Field Consortium. And the aim of the Open Force Field Consortium is to set up a force field that is available to everyone free of charge. And it's still in its very early stages and is being developed, but we are beginning to incorporate it into FLAIR as a possible option for the simulations. And sometimes what you find with force fields is they are very extensive and they do lots of really nice stuff. But you always have a project or ligand that's not described particularly well, and if you've got a torsion parameter within your ligand that isn't well described by those force fields, we have the ability to in FLAIR the scientist has the ability to generate custom force field parameters so that description can be better represented. So what happens there is that you define the torsion that you want to have edited. You do run a quantum mechanics conformation trace, and then the program then aligns the energy of the new force field parameter to the quantum mechanics trace, so that torsion is a lot more accurate when you start the molecular dynamics run. So let me go and move on to molecular dynamics within FLAIR. So
So the other thing you can do is you can define the molecular dynamics as having explicit solvents, so that's water molecules, or implicit solvent, which tends to be things like the sort of the Born approximation, so just a reaction field approximation. And what you can do once the MD simulation has completed is plot the root mean square deviation from the starting point for the dynamics run, and we have a player which can then browse through the frames, so you can basically so this is when the molecular dynamics has been completed. So here you would have your trajectory, and in this trajectory you have the plot of the root mean square deviation from the starting point, and so this will give you start to give you an idea of how stable your system is. And you can have this blue line defines where your current frame is, and you can redefine what root mean square calculation is done. So by default it's done on the whole system, but you can actually define just the visible atoms, a subset of visible atoms, and recalculate the RMSD just for those visible atoms. And what that means is if you want to home in on the ligand and see is it the ligand which is moving quite a lot or not moving a lot, you can just highlight the ligand and recalculate the RMSD to see how stable that is. The other thing is, so we have this player here. So basically what this allows you to do is it can play you the snapshots of the molecular dynamics, and you can decide what sort of steps you want. So you can sort of go in 1 step or 10 time steps or 100 time steps, depending on how, well, I guess depending on how how long your MD simulation is. You can run simulations from 10 nanoseconds or even less if you like. I've run simulations up to 200 nanoseconds. So you have the ability to decide how you want to run these MD simulations. We also have some analysis tools. So as the MD simulation progresses, you can keep an eye on for each of the snapshots how your hydrogen bonding is and how your aromatic sort of interactions are taking place as that simulation progresses. So as it progresses, you may find that you lose the hydrogen bond, or you may gain some new hydrogen bonds, and so you can you have this way of looking at the dynamics and looking at how this changes as the trajectory regresses. You can by default the weak hydrogen bonds are turned off, but you can turn them back on again, and you can basically look at the trajectory. So you can look at what part of the trajectory you want to look at. In that part of the trajectory, at what point, how many frames is that hydrogen bond present for? How many is it not present for? And so you can define which part of that trajectory you want to analyze. My last section for the flare part of this talk is to briefly talk about Python. Now, Python is a program for scripting program and scripting language, and it underpins the whole of what flare is. So what this means is that you can actually script your own Python jobs to run within Flare. We have an interpreter within the GUI which allows you to do that. Or if you've got single commands, we've got a console which you can write those single commands on. And we have full support for extensions through Python modules.
And we also have the integration through the RD kit as well. And what you can do with this is that you can customize existing tab menus as well, so that if there is something that you that you use quite regularly, you can introduce a new tab with those new functions. And the other thing which we have is some Python extensions. So if you're not a Python expert and you want to look at some extra functionality, what we do is we ourselves have generated some Python scripts for features which are not initially incorporated into Flare, but are downloadable from this GitLab address here, and you can install these, and these will include a number of nice features which are not initially installed. Things like calculating the RMSD, for example, between a doc solution and the crystal structure. I've used that quite a lot. It's useful. Or you can just, if you want to plot something, so say the electrostatic complementarity against the activity, then you can use the plot function here. And there are a number of other tools that are very useful. The other thing which we have is associated with these extensions is command line extensions. So sometimes what you need to do is quite a lot of work, and so maybe several thousand molecules, and that starts to become for any GUI, that becomes more of a hindrance, and very often you'd want to look at running these things on the command line. So you can do this through these command line extensions, which are provided as part of the Python extensions. So just to summarize on the Flare part of this presentation, so what I've done is to give you an introduction to the CRESSET science and software, and I've walked you through some of the features we have within Flare, which I think will be very useful as part of the hackathon project, in terms of how you bring in ligands, how you prepare proteins, what you can do with the ligands and proteins once you've got them in there, and and I've given you sort of an overview of the binding site water analysis, the biomolecular simulations, and I hope that has been very useful for you. What I want to do now is I want to move software, so I'm going to move from Flare to Spark and give you a brief introduction to what Spark is. Okay, so we have this Spark is a bioisotope replacement program. A lot of our customers are really happy with it, and certainly one of our customers was extremely happy and said it was the best isotope application on the market. And basically, it's there to help you generate some new ideas. Maybe why would you want to generate new ideas? Well, maybe the existing molecule, the core isn't ideal. Maybe the patent space is crowded, so maybe you need to develop that in terms of moving away from patent IP. And so you can use Spark to change the core on the top, like I've done on the top here. So we've replaced this single ring here with an aromatic system, and or you can use it to add R groups to an existing ligand. And what we can do with this is the way in which the program works means that you can do a fragment replace it, and then determine whether the molecule which you've generated is similar to another molecule and another potential ligand in your that you're interested in. And so what you can do then is to start to build ligands which begin to look like other ligands in your project. The other thing you can do is you can look at fragments, and you can either grow from a fragment, or you can have two fragments in place and grow and link them together. You can also replace crystallographic water molecules, and you can also do macrocyclization. Spark is you can use Spark either as a GUI or as a command line, and it's so the ability to generate your own database of fragments that Spark uses to build these molecules is also available to you. And just like in Flare, the GUI has the ability to generate radial plot properties, so you can prioritize your design molecules using a multi-parameter function. So one thing I didn't quite make clear is that so the way that the Spark works is you give it an existing molecule, and you say to it, well, I want part of this molecule replaced, and I want you then to compare the field points of the new molecule with the field points of the existing molecule, and show me how similar it is. And we do this from, so we could have done this from a fragment point of view. So just consider the core fragment in this case. But actually, what's important here is that actually, because of the way in which the Z force field works, it means that we have knowledge of actually what that cause effect is on the rest of the system, which means that actually these sort of smaller charge regions that are not part of that fragment are actually altered slightly, which means that if we were just simply considering the fragment alone, we would probably not get a correct result. By incorporating the description of the whole system and the way in which the charge distributions change throughout the whole system means that we get the opportunity, we get the chance of getting a result which looks more like, from an electrostatics point of view, looks more like the original molecule. And what that means is that you can, because we're doing this sort of full molecule comparison, it means that we can easily do fragment growing and linking. We can easily sort of look at water replacements. We can easily score, as I've just mentioned, we can easily score the new molecule against another molecule rather than the one that we're editing. So there's lots of opportunities by scoring on the whole molecule. The other thing we wanted to do with Spark is to make it as easy as possible to set up an experiment. So what we have is these wizards, so that you can decide which of these experiments that you'd like to do. So you might want to do bioassisted replacement, or you might want to do ligand growing, or join two ligands together. So by selecting these from one of these wizards helps you set up the program correctly for that particular job. In addition to that, there are some other functionality so that more expert users can access the sort of features within the program, sort of how many compounds are returned, for example, how they want to score the compounds compared to the original molecule, if they want to start excluding or including particular smarts features. So if you find that you do some initial work and you find that there are some compounds coming back which you don't like the look of in terms of the smarts, some of the smarts options. What you can do is you can define the smarts that you don't want to see in the output, rerun the job, and get another set of 500 molecules where that substructure is no longer there. So so in terms of the resources for Spark, so basically what it's doing is when it's doing these replacements, it's using an input database of fragments to connect to you know, the existing molecule. And so if you're looking at cores, then what we have is a list of commercially available catalogs and Chembl, and we have basically fragmented those up into an input database. And as we've fragmented those up, we have an understanding of the way in which, how many times each of those fragments has occurred. And so what we have here then is the ability to say, well, actually that fragment has occurred a lot of times in the initial compound set. That must mean that there must be some increased synthetic tractability with that, compared to, say, having only one. If that fragment only occurred once, then that might start to ring alarm bells that actually that fragment might actually be very difficult to make. So we have a proxy for synthetic tractability based on how often those fragments occur within the input database. So when we're looking at adding R groups, we use the databases from eMolecules, and what happens there is that you have defined chemistries. So you find that the reagents have been binned into particular chemistry sets, and that you define which chemistry you want to have at which R group. And these reagents sets are updated on a monthly basis, and most of the R group chemistries are covered. But so, for example, we have primary amines and carboxylic acid motifs which are looked at. Also, we have the ability for you to create your own databases of input fragments. So if you have fragments which no one else has that are important to your project, what you can do is you can take your input molecules and fragment those up and incorporate those into the input of Spark. So the reason why you'd want to use Spark is just so that you can get some results which move you away from the obvious solutions to something that's perhaps a little less obvious and perhaps even more novel. When you have the ability you want to sort of move away from existing patterns, and you want to sort of map out what sort of chemistry there is available. So you want to sort of generate leads from patents. You want to help lead optimization so that so you avoid less obvious ideas and think of something a bit more novel. You can take the reagents that you have in your existing stock and apply those to your scaffold and identify which of those reagents look best to use for generating some new ideas. And you can also use it to start to consider perhaps a backup series from your existing project. And what you can also do here is, by eliminating some of the toxic substructures in Spark in the design at this stage, that can start to reduce the risk of late-stage attrition as well. So the other thing I wanted to talk about is that also we have, as I just showed you, the sort of wizard, so that allows you to set up the job very quickly and get some results very quickly. And the other thing which we have is that Spark is available with a GUI, a command line, and we also have options for Nyman pipeline pilot workflows as well. So that is a brief introduction to Spark, and I'm now going to sort of move on to Forge, which is our ligand-based drug design software. Now, Forge is used when you want to decipher structure-activity relationships with. Maybe you don't have a crystal structure, but you have some ligands, and you want to know how those ligands change, how the activity of those ligands change with their structure. You can use Forge to predict quantitative structure activity models, but you can also do that from a qualitatively point of view as well. And what you can do with Forge is once you've got these models set up, you can then you can use that to design and score incoming molecules, or perhaps a small selection of molecules in 3D to determine whether they have the appropriate electrostatics and shape information to help the SAR. So the other thing, again, like with Flare and Spark, is that as part of Forge we have the ability to do radial plots and multi-parameter scoring. And what we can do is use Forge to look at to do some virtual screening based on the scoring of the electrostatics and shape of your known hypothesis, or against your prepared QSAR model. So one thing you first need to do in Forge is to do a ligand alignment, and you can do that with the CRESSET science of the said force fields, and you can define the electrostatic and the shape of those molecules and overlay them, or you can use a substructure point of view, so that if all your ligands have a common substructure, you can get Forge to align all the molecules based on that substructure, or you can do a combination of both. You can also apply some constraints to bias the alignments. So again, if there are some said fields which are important as part of the overlay, you can ask Forge to use those, and you can also use pharmacophore constraints as well. So if you're interested in sort of hydrogen donors and acceptors or aromatic points to be at certain points, then you can also define that to help with the overlay process. If you do also have the protein structure available, then the other thing you can do is incorporate that protein structure and use the excluded volume so that the alignments don't grow into the positions of where the protein atoms are. So one option with Forge is what we call field QSR, and that's where we take the aligned structures and we generate a quantitative structure activity relationship based on that alignment. And so what you get out of this is a quantitative model, but also you get the knowledge of the overlays, and you can use that knowledge from the overlays to determine which of those features are good for activity, which of those features seem to be detrimental to activity. And so you have the best of both worlds. You have the ability to run your molecules through the quantitative structure activity model to get a score, but you can also use the alignment to determine what features are probably best. The other thing you can do in Forge is machine learning models, and that involves that includes regression and classification based models, and for that we have a number of enhanced models that are available, like K-nearest neighbor and random forest, and you can also automatically build and report back the best models that are generated. So in this case, this is a bit different to the previous case because you do get quantitative structure activity models out, but what you're not sure about is why those models are actually working. In the previous case, the field QSAR, you have the ability with the alignment of the molecules to see what parts of that structure could be contributing to the activity. The other thing which you can do in Forge is to look at your data series and understand, use it to understand where there are the places in your SAR where you have large changes in activity as a result of small changes in structure. And these are very interesting areas because you'd want to think, or you can use Forge to then start to ask the question, why is that? What change? What is the change that's happening here? So Forge can be used to identify where these activity cliffs are and why these cliffs are taking place, and what can we do to improve upon that. So the other thing you can do with Forge is look at things in a qualitative way. And so what you can do is you can basically take your aligned ligands, and you can what the program will do, having taken also the activity, it will show you regions in space where you'll get activity if you have a positive group in this particular region, if you have a negative group in this particular, a negative field in this particular region, a positive group in this positive field in this particular region, and it can also show you at what points where if you had some steric occupancy here, for example, in the green section, that you'd probably get some favourable benefit for the activity, but the magenta, if there's any atoms that go into that region, that will probably result in decrease in activity. So while you don't have the quantitative aspects here, you have a qualitative view of what sort of functions at what points of the molecule are likely to give you good activity. Now, another thing in Forge is that sometimes you don't have knowledge of the bioactive conformation of your ligand, and so you either don't have a crystal structure or you don't have any SAR to help you, and you just know the 2D structure. So what we can do here then is to generate 3D conformations of the ligands that we're interested in, identify the field features that each of those ligands, and we can then generate a number of overlays which you can then use as the basis for determining whether where highly active molecules are being overlaid onto one another, which of those features seem to be most important. And so you can set up if you like, quite a complex description of what features in terms of the electrostatics are important for what seem to be important for the molecule design. So the other thing that Forge gives you is the ability to understand what you see from a protein's eye view. So So if you have an existing ligand, for example, that has a highly positive field area and a small negative field area, if you start to edit that molecule, you know that actually to retain that kind of activity, that's the sort of features that you will want to see your new molecule have. So using Forge in this way allows you to generate new molecules which have a similar protein I view to existing ligands. So basically what that means is that what Forge can do is that you can use it to apply 3D modeling techniques without target information. You can improve the ligand design by using a 3D description. You can use it to try to give you better understanding of the SAR data. It gives you the ability to generate predictive models based on the activity of your data and your structures, and basically it should help you improve the communication for new ideas across the team or across other customers. And again, like Spark, we have a wizard so that when you open Forge, you choose what you want to do, you set up the job, and then you run, and then you get some results which you can then use. And hopefully what that will mean is that you spend more time on the science and less time about how the software works. And like Spark, we also have the GUI in the command line and some Python and Pilot workflow solutions as well. So what that means is that what I've done today is to briefly talk about the CRESSET science and how that is described. I've talked about at some length FLAIR, which is the structure-based drug design program, both in terms of bringing in ligands, bringing in protein molecules, and doing some functionality within that in terms of like docking and electrostatic complementarity and water analysis. I've then gone on to talk briefly about Spark and what that involves, and also Forge, which is the other ligand-based design tool, and I realised that this has been quite a whirlwind of information, and I'm sure that in future there'll be time to look at these in greater detail. But I hope today has been useful for you. I want to take this opportunity to thank the organisers for giving us the opportunity to showcase our software to you today. I also want to thank you very much for your time as well. And again, I hope you found this useful. Thank you so much.
Thank you so much, Stuart. This is Giri this side. So we have few questions, and I'm also appreciate your time for delivering your ideas as well as the capabilities of the CRESSET tools. And also I like the statement, all this process is being done to reduce the risk of attrition, the later attrition. So
yes,
we want to be sure with the confidence to move forward with the next stage. So let me take a few questions, and either you or Krish can decide who wanted to answer. So the first one, in the radial point view, what does the green color indicate?
Okay, so the green color represents. So let me go back to that slide because that might be quite useful to talk about. Just bear with me for 1 second.
Please go ahead. No problem.
Let's try and find that slide. There we go. So what is the green color here? So let me just bring this back into PowerPoint view. So actually what the green color here, so it can actually, depending on how you set up the system, it can show you how much. So if your molecular weight is if it's important to have a large molecular weight and a small molecular weight, this represents how much of that feature that molecule has, for example. So if you have, for example, a molecular weight of 300, you want a molecular weight between 350 and 500, for example, and you had a molecular weight of 360, then for the molecular weight part, the green will be represent where that molecule occurs in that range. And so you have sort of here you have a pentagon because you have 5 different properties. And so one of the properties may be at the maximum point. One of the properties might not have anything. It might not have anything in that range. So in these plot properties, what you have is you can define what ranges you want to see. So in this case, the molecular weight between 350 and 500. So if it's lower than, if the molecular weight is lower than 350, it will mean that this section will occur at the center. Well, actually, it can be both. You can set it up so it can either be so that the lower value happens at the center, or the lower value happens at the extremity, at the edge. It's up to you.
Okay. So I think you already answered this question also. What is the expected range of different properties in the radial plot? I think you just answered it. But
yeah, you can. It's up to you actually. It's that you have full control. So for example, you might want to be on a project where you're looking at lead-like. So you may want to be looking at molecular weights where you're looking at between 200 and 400 molecular weight, and not 300 and 500. Yeah, 350 and 500 molecular weight. So you actually have full control as to what you want to see, and you can so you can define that both for molecular weight and for SLP, and also if you want to bring in your activity, so say you may have your activity values in an ST file, you can also use those activity values. So if you had something, you had some compounds at millimolar and some compounds at nanomolar, you may want to identify sort of the ideal range of activity between nanomolar and micromolar, for example.
Okay. Another question is that if one has a flare license, can the user perform MD simulations for free?
Krish, I think I'm going to let you answer that one.
Yeah, so we have different licensing options for Flare. So we have basically Flare Essential, Flare Designer, and Flare Professional. So the Flare Professional license is the one that has access to MD simulations. So yeah, so basically for the project, looking at the problem statement, we'll have to issue the appropriate license. So the people who register with us, if they can share what problem statements they are addressing, that will help us to provide the right licensing to them.
Okay.
So yeah, so to answer the question, if we provide Flare Professional license, yes, they will have access to MD simulations.
Okay, great. And another question, how much time do you have any benchmark on that, how much time it will take to run 10 nanosecond simulation on a particular configuration of a computer for MD simulations in Flare?
That's a hard question to answer because it will depend on how big your model is. I think it's a good question because I haven't got anything to hand. I think 10 nanoseconds would. I'm just trying to remember the training material that we did, and that was a relatively small protein. I can't quite remember the size now. And that took. I can't honestly remember. I think it took about 24 hours. But let me. Is there a way I can sort of come back to you with some answers on that?
Absolutely. Yeah. So the person who have asked, kindly please write to CRESSET directly. Already Stuart has showcased the email address at the end of the slide. And I'm going to the next a few questions. Like if we are considering covalent docking, so does the ligand dock to the protein? Does it show any understanding of the stability of the reaction?
Interesting question. So it's basically done on a knowledge-based system. So basically it says if your ligand has that particular electrophile, you then in the covalent setup you define which residue is going to react with that. So you don't have knowledge of how strong that bond is, but what it will give you is whether that, once covalently docked, whether that ligand can actually occupy that binding site, and you can also define with some help if there's some electrophilic groups that are not on that list. If you write to support at CRESSET, we will be able to define that new electrophile for you, so that can be incorporated. And what I have found also is that if your compound has more than one electrophile, then it will be the, so we have it in, if I go back to the docking. Yeah, so if you go, so if you consider this list of these lists of the electrophiles, there's an order of precedence here, and the ones at the top will be prioritized over the ones over the a bit further down, which means that if your ligand has two electrophiles, it will be the one which is highest prioritized, which will be reacted. Now, if that's problematic, then what you can do is write to CRESSET support, and we will provide you a file where that order is changed, so that you can then define the electrophile that you want to see reacted.
Okay, right. I'm going to the next question. Do you have 9 nodes for flare modules?
That's a great question. I believe we do. I will double check. I will double check and write back to you.
Okay, fine. Another question. Can one use template docking for a protein which does not contain a co-crystal ligand?
Okay, that's an interesting question. So you would use template docking if you know if you knew the binding mode of the ligand. So you may, for example, if you have an apo structure which has no ligand, and you then bind into that apo structure a ligand that you are very familiar with, and the docking solution then comes back with something that you think is you're absolutely sure that is the correct answer, then what you can do is use that dock structure as the template for future dockings. So yes, you can do it, but the question is, does it make sense? And I would probably suggest that it doesn't. But if you wanted to do what I've just suggested, then you can absolutely do that. Yes.
Okay. The next question is probably for Krish.
Yep.
How do we get access to the CRESSET software for during Drug Discovery Hackathon?
Okay, great. So we will be providing licenses for all the participants who are registered for the hackathon, and we will be doing that through the organizers. So what we have done is we have made a registration link that we'll send out to the organizers, and they will in turn send it to the participants, and whoever registers for CRESSET software will get the licenses as well as a follow-up training session on both Flare and Spark. So yeah, so please contact the organizers, and they'll be able to help you with that. So we'll be in touch with the organizers, and we'll provide the link and the licenses through them.
Okay. Thank you, Krish, for that. That's all for today evening.
I'm sorry, Giri, just one. Yeah, one. I think Stuart has already shown the slide with the email address. So if anybody wants to contact us later on with any questions or queries, please feel free to do so.
Yeah, absolutely. So as Krish mentioned, I want to just add on. All of you, please kindly wait for the official registration link for Drug Discovery Hackathon. You will have all the details later on with the drug discovery virtual tool room, and also how to get access to all these tools from the partners. And I take this occasion also to thank Stuart to taking time and also share his views as well as the capabilities of CRESSET tools once again, and also thanking Krish as well as other partners of CRESSET in India, and and also thanking the members of the DDH training team from NIST, Jorhat, headed by Professor Narari Shastri, to all the participants who are enthusiastically waiting for the registration forms. There are already guidelines for problem statements, and resources for problem statements are already published in the Drug Discovery Hackathon website. So kindly go through that to just have an understanding, and all the problem statements are also listed in the website. So you're already having the data which is required for you to start working on. Let the registration links come in, but you already have the problems that is being already listed. And there will be more sessions coming up on following drug discovery areas and techniques and methodologies in the upcoming days. And these are the official links for drug discovery hackathon website. The training sessions always will be in MHRD Innovation Cell. All the previous sessions are also available, and the training website is on NIST website. You can register if you want. You won't get any acknowledgement email, but you will have an acknowledgement number. This is just for accounting that you have registered for the training. If you're later you want it for certificates or others. About the do's and don'ts about the drug discovery hackathon for a participant, how to participate, what are the conditions that you have to consider. All those things are being given by Dr. Abhay Jere in his YouTube channel. So that's all for this evening. Thank you all. Thanking you all listeners in YouTube as well as in Facebook. And have a good evening. Thank you.
Thanks a lot, Giri.
Thank you,
Bye.
Giri.
Yeah, bye, Stuart. Bye.
Bye-bye. Thank you.
Thank you.